This video serves as a brief overview of the MECH 532 research project. This project tasks us with the conceptual design of a fixed-wing aircraft, accounting for a set of constraints and required performance characteristics. We proceed first to talk about the design methodology that was followed. Designing an aircraft is not an easy task due to the great amount of variables involved and interactions between them. This combination results in a complex conceptual design stage. Aircraft design benefits from a long history with a large set of well-documented material, mostly focused on large commercial airplanes. While this is great reference, this is not the goal of the project, so we select a simpler, more general design methodology to follow. The benefit of following one such methodology is that it helps in establishing goals, fundamental design stages, and perhaps most importantly, criteria with which to identify and compare solutions. We adapt a design methodology commonly found in mechanical engineering problems. This process is roughly divided in 5 steps. The first stage is focused on understanding the problem at hand and translating it into engineering language. This requires extracting the requirements from the problem statement and to study relevant sources to identify quantifiable methods to evaluate these requirements. In the next stage, we study techniques that have allowed these problems similar to this one to be resolved in the past. Various design manuals, textbooks, and procedures are consulted before initiating the design process. The goal of the preliminary design stage is to obtain the basic layout of the aircraft and its primary configuration as a starting point to start the process of design evaluation, redesign, and optimization. The next stage consists of evaluating this preliminary design and making necessary adjustments for a feasible solution. This stage starts using XFLR, the analysis tool which will be used extensively along the project, so research on its use, in other words, what it can and cannot do, is required. The result of this stage is a design that can be analyzed with the tools available. The next stage is iterative and will be the core aspect of the project. We choose to work focused on achieving individual targets, or specifications, in order of their perceived importance. For example, no tail analysis will be performed until the wing, whose main function is to generate lift, behaves according to the specifications. This approach is perceived as intuitive, since identifying root causes of problems that arise is clearer this way. Since making modifications on components further down will inevitably result in changes in previously resolved functions, going back to evaluate them and adjust previous steps is inevitable. Finally, the overall design is evaluated against the design targets, and minor adjustments are made if deemed necessary. Out of the design requirements, we identify weight and endurance as our most important targets. Maximum endurance is achieved at minimum power conditions, identified by the relationship shown. At each stage in the design, the endurance rating and weight will serve as the main comparison with which to judge otherwise similar designs. The stability of the aircraft will be studied through the stability derivatives in the static sense and through model analysis for dynamic stability conclusions. We are also tasked with returning to the same airport the aircraft started at. This in turn shapes the mission profile. The mission profile is conceived to achieve the aforementioned constraint and to maximize endurance as much as possible. It starts with a climb to the target altitude, followed by a cruise flight at 15 meters per second. 2 bank level turns are performed, one for 270 degrees and another one for 90 degrees in the opposite direction. This ensures the aircraft gets back on the same flight path, so the initial airport is reached. The aircraft cruises again at 15 meters per second and drops without thrust in a glide to further increase airborne time.
Now we will be discussing about preliminary design and analysis. The flow of the stage can be seen here. For the wing, we chose these Epler, NACA, and Selig airfoils and compared them in XFLR. After the analysis, Selig 6043 was chosen, and for the tail, after running analysis with different symmetric airfoils, NACA 0012 was chosen. With these airfoils and the geometry, we made some iterations in MATLAB and finally selected a design which was analyzed in XFLR. The analysis showed that the aircraft was not longitudinally statically stable, and moreover it was flying at negative alpha at 15 meters per second, which was not acceptable. It was believed that we need to work on our wing and focused on wing design thereafter. After running the analysis with modified wing, it was compared, and it can be seen that the issue of flying at negative alpha was solved. However, alpha stall was low. With an effort to decrease aspect ratio in order to increase alpha stall, the chord was decreased and another iteration with decreased span was analyzed. After many iterations, we finalized a wing with low alpha trim, good endurance, and stall characteristics.
After the wing was finalized, the tail was added to the design. The design was analyzed and it was marginally stable and really far from trim conditions. Furthermore, various iterations with different tail area, tail arm length, and CG locations were made with an effort to achieve trim conditions. stability, and high endurance requirements. Finally, the design of the aircraft was finalized, which was longitudinally statically stable, had high endurance, and was trimmed as per mission requirements. Now, let's talk about stability analysis. First, let's discuss about the dihedral and understand its requirements in the design. Once we ran the stability analysis and checked the log file, it was observed that the aircraft wasn't laterally stable. Due to this, the dihedral was introduced, which made the stability derivative as desirable. The following modes were analyzed in the analysis.
First, we see the SPPO mode, and we can see that it behaves as desired. It almost damps out instantaneously. Next, we analyze the phugoid mode, which is another kind of longitudinal mode. We can see that the amplitude of the oscillations is relatively decreasing. Since it's going to take a while to return to its equilibrium position, a part of the entire mode is shown. Next, we see the roll subsidence. It can be seen it is stable, and we've shown the analysis at different speeds. Next, we analyze the Dutch roll. It can be seen that the design is stable, and at this mode the analysis was done with a different speed to analyze the motion. The root locus graphs were then analyzed. As we can see, the poles of the longitudinal mode are positioned as desired. Even for lateral mode, it shows acceptable root locus plot. Also, the time response plot of all the modes shows stable and favorable characteristics. The SPPO and roll subsidence get stable almost instantaneously. The phugoid shows convergent behavior, and the Dutch roll also damps out quickly.
We will now talk about the fuselage design and its impact on the performance and stability of the aircraft. Basically, the fuselage main goal is to hold the wing and tail together and protect internal components of the aircraft. So far, we performed our analysis on the wing and tail only and ended with a stable aircraft at cruise. Therefore, we know where the battery, payload, and motor are located, and so for the tail. We also know what these components' dimensions are, and so we are now able to do an initial sizing of the body. Furthermore, as we want to optimize weight, we design it as slim as possible, as you can see on the image. Now the question is, what are the performance and stability of our aircraft if we add this fuselage into our analysis? The important thing to keep in mind is that XFLR doesn't recommend to do this, as it may lead to inaccurate or false results. Nevertheless, we decided to perform the analysis anyway, to have a rough idea of how the fuselage is changing the performance and stability of the aircraft. So we ran our analysis and compared the results with the previous one. We immediately noticed a huge drop in endurance ratio and that the aircraft is no longer trimmed at 15 meters per second. After a quick review, we found out that it is mainly due to the wing position, not high enough, and therefore a lot of turbulence were induced, as we can see on this image. We fixed this issue by raising the wing until the top surface is completely clean of the fuselage. As you can see now, the new configuration results are way better, and it even provides slight improvement in endurance compared to the bodiless design. The aircraft is trimmed at cruise, and the stability derivative shows that it remains statically stable, with an improvement in LV, the roll moment due to side slip. Overall, this design shows a good potential, and therefore it will be considered the final configuration for the design project. To conclude, this project main goal was to perform the conceptual design of a fixed-wing aircraft, accounting for a set of constraints and performance requirements. Following a design methodology, we arrived first at a preliminary solution, which has been then systematically evaluated and corrected using XFLR, mathematical principles, and intuition. The result is a stable aircraft, with a focus on an endurance-optimized steady level flight at a specified cruising speed. However, we found that the main issue is that the weight is not realistic considering a 1.5 kg per meters cube foam density, and that the aircraft is undersized compared to the motor characteristics, ending up with a 10-hour endurance time. A future iteration should consider increasing the wing size to reduce wing loading. This will naturally result in an increased weight and also more drag due to a larger surface, in turn dropping the endurance to more realistic values due to an increased motor energy consumption.